Hey everybody! So last week we started our exploration of neural networks looking at just a single neuron in an algorithm called the perceptron learning algorithm. Today we're going to hook up a bunch of perceptrons into a multi-layer perceptron, which is a very well understood and well-known type of neural network. It's now become, in recent times, known as a deep learning network. We're gonna learn about that word that you may have heard of. Let's take a quick look at the differences here. So if you take a look at the handout, if we start here in section 1, this is a picture of the kind of neuron that we were looking at, the kind of artificial neuron that we were looking at last week. This one has 4 inputs, x1 through x4, 4 weights, weight 1 through weight 4, and it has a threshold function that is what's called a step function. So basically there's a threshold, and the activation, which is the sum of the weight times the input, the activation builds up and builds up until and it's still outputting 0 until it reaches the threshold, and then the output jumps up to a 1. So if you were to graph that function with activation down here and the output on the so activation on the horizontal axis, output on the vertical axis, it would look like this. In fact, it wouldn't even really have a line there. It would just be 0, 0, 0, 0, 0 up to the threshold. Then it would suddenly jump up to 1. So that's called a step activation function. So the output is either a 0 or a 1. The inputs, however, we allowed to be any number, although we generally thought it was maybe a good idea to keep them between 0 and 1 as well. Okay, and we learned that this type of neural network architecture, just a single neuron, has a hard limit built into it about what it can do. It's a linear classifier, and we can prove that pretty easily to show that the equation that it uses to classify is the equation of a straight line. So if the task can't be reasonably separated by a straight line, if the points in class 1 and class 2 don't easily separate by a straight line, it can't be expected to do very well. Now that was I think I told you guys a little bit about the history. That was kind of a sticking point for a number of years through the 80s, through the 70s and 80s, until sort of multiple people discovered that it would be possible that there is a training algorithm for what's called a multi-layer perceptron. So this is a multi-layer perceptron, aka a deep learning network. If you take away, if you take a look at it here, what you can see is these are the input units, 1, 2, 3. So this one has 6 input units. It has the output layer here has 1 unit in it. Sometimes we call them units. The artificial neurons are sometimes referred to as units. The output layer is still one thing. So it's going to output a 0 or a 1, or it's going to output actually close to a 0 or close to a 1. That's one thing that's different about multi-layer perceptrons, and one change that we have to make throughout the network, which we'll talk about later on, is that the activation function can't be a step function. The final unit could actually be a step function, but the ones in the middle can't be for mathematical reasons. So typically speaking, it outputs a number between 0 and 1, which you can use to represent a classification. Basically, if it's 0.5 or less, then it's a 0 classification. If it's more than 0.5, then it's a 1 classification. You could think of it that way. And you could also then read some confidence off of it. If it's really close to 1, then it's probably pretty confident. If it's really close to 0, it's probably pretty confident. If it's in the middle, hovering around 0.4 or 0.6, maybe that's not the most confident classification. But what makes this multi-layer perceptron are these hidden layers here, these units. So these are like they are similar to perceptrons. So you can see, and the layers are fully interconnected. So you can see that, for example, take this neuron here. It has a connection coming in from all the neurons in the input layer. This one also has a connection coming in from all the neurons in the input layer. And so these neurons do some processing, and they work exactly like, pretty much like the perceptrons that we've seen before. They multiply the weight of the connection times the input, sum that up, and then output something. But they don't have a step function. They output usually a number between 0 and 1, but sometimes a number between -1 and 1, and so on. There's different functions. And their output then gets fed forward. So these are sometimes referred to as feed-forward networks. It gets fed forward to the next layer, or the next hidden layer, as they call it, of neurons, Notice that each one of these has a connection from each neuron before it. And these ones also perform. They figure out the amount of activation, and they have an activation function, and they will output some number between in their range, 0 to 1 or -1 to 1 or something like that. And then these feed into the output layer, which in this network just has a single neuron in it. And then this one here is basically a perceptron. It's just computing the activation, figuring out the output, and giving us the output. So you can view this here as a perceptron, and this down here as this is the input layer, and these are the hidden layers here. Okay, so there's a bunch of terminology here. So multi-layer perceptron is sometimes called MLP, or a deep learning network. Okay, there's the input layer and the output layer, and the layers in the middle are called hidden layers. The activation always goes in one direction, so we're always moving. Usually they're drawn from left to right. So the input layer is here. It feeds forward, feeds its activation forward to this layer, which computes its activation and feeds it forward to this layer, which computes its activation and feeds it forward to the output layer, which gives us the output. So because of that, these are sometimes referred to as feed-forward networks. We've got here, we usually have a lot more connections because the layers are fully interconnected. Every neuron in the layer to the left connects to every neuron in the layer to the right, feeds its connections forward. That's not true in so-called convolution networks. So there are other architectures that aren't fully interconnected, but the ones that we're going to be dealing with are just going to be fully interconnected. This one has 39 weighted connections, and training the network consists of, just like in a perceptron, small changes using a learning rate to those weighted connections. And the problem that held things back for a little while was when we were training, if we just had this layer here, right? So we imagine this was the input layer. We feed forward to here, we get our solution, and we can see whether it was correct or incorrect. And then we can look back and we can say, well, this node here was giving a lot of activation, so it was quite responsible for the error. This one was giving less activation, so it's less responsible, and so on. And we can kind of easily see whose fault the error was, and then tune the weights accordingly. Remember, we do it by multiplying the learning rate times the input, and so what that has the effect of, if the input was high, changing the weight quite a lot. If the input was low, changing it not very much. If it was 0, changing it not at all. But the problem then is, back here, we need to train these weights as well. So if we have a multi-layer perceptron like this, we can easily tell what went wrong at this layer and who was responsible for the error. But back here, it becomes much more murky because we don't know what the correct output for these nodes was. If we knew that this one needs to output a 1, for example, then we could go back and we could look at these inputs that it got and train these weights, the weights that are coming into it. But we don't know. That's the whole point, how the network should work. Otherwise, we would just fix the weights. We need the learning algorithm to explore and to find those values. So because of that, we're able to train this layer of weights, but then we're stuck on this layer because we don't know what the target output of these nodes is. And that was kind of the sticking point. And same problem back here. We don't know what these nodes should be outputting, so we can't easily train these weights that come before it using the same algorithm. So what was kind of discovered by multiple people, including Rumelhart and McClellan. Rumelhart, I think it's Rumelhart, eventually got hired by Google when deep learning networks took off in the 2000s. But he was a pioneer. Rumelhart, I might be getting the name wrong. I'll have to look it up. It's either Rumelhart or McClellan that is still around, quite old now, and working for Google as kind of the godfather of deep learning networks. They and other groups, but they became famous for it, rediscovered this algorithm where what you basically do is you back propagate the error. So the feed-forward network feeds its activation forward like this, and then we figure out at this layer how much error was there, and then we propagate that error signal backwards. And you can prove with some complex math that involves differential equations and so on, you can prove that this works. So basically, you look at how much error was this thing responsible for, which we can kind of get an estimate of. and then you use that to modify the weights that were coming into it. If this was responsible for a lot of error, then we modify that, and then we go back here and we do a little sum to figure out how much, how much did this guy's, and what it comes down to is how much did this guy's weights change, the ones coming out. And if they changed a lot, then it must have been responsible for a lot of the error, and so on. So we take, what we do is we go forwards, we figure out the error, and then we back propagate. We go backwards, propagating the error back through the network, assigning responsibility to each node as we go. Okay, and the math of it all is beyond the scope of what we're doing here, but you can figure it. You can go and look it up if you're really interested. We're not going to program this ourselves. We're going to use sklearn when it comes time to actually do the programming. Okay, so the output layer is a linear classifier. So so this is something else I wanted you to notice. So what we know is that multi-layer perceptrons can learn a decision boundary of any shape. They're not just linear classifiers. Okay, so they are. As long as you have the right configuration of hidden layers, and there's a bit of an art to getting this right, and the right activation function, a bit of luck in choosing the random starting weights. So we usually start with small random weights, and enough time. If you have if the stars align and the planets converge, then your network will converge. So converging means it comes to a solution that hopefully is a pretty good solution. So deep learning networks that do image classification tasks, they have a slightly different connection. They're still feed-forward networks, but the connections between the layers are a little different than what I showed you. These are the so-called convolution networks. But it can have thousands of inputs, hundreds of hidden layers, and require thousands and thousands of epochs of training. So one year I did an IBM Watson workshop with some students from this course, where we trained IBM Watson, which is sort of a cloud-based deep learning network, to categorize, was it dogs, I think? Dogs from non-dogs? I can't remember. But, it took a long time to train it, like hours to train the thing. So it takes a long, long time. But it can learn any shape. It's not bound by a straight line. You can learn any shape, in theory, if you have the right configuration and blah, blah, blah. But I just finished telling you, and this is the thing to notice, I think, to really understand how these things work, or to get a gut feeling for how they work. I showed you this is basically just a perceptron right here. So you could easily prove that this part of the network, just if you just think of this layer and the output layer, this is a linear classifier. So whatever these three nodes, if it learns to do the task, let's say this network works and it's a nonlinear task and it learns to do it, the last part of the network is a linear classifier. So what's happening, what must be happening, is that the input, which can't be classified in a linear way, is being transformed at each layer until we get to a new representation of that input, which now can be classified in a linear way. So individually, each of these neurons is just a linear classifier. Each one of them is drawing a straight line, but somehow through a little bit of math, they're combining these straight lines together to get us an arbitrarily shaped decision boundary. So another way to think of that is that we are transforming the input. From this layer, it gets transformed to another layer of neurons, which represents it differently, and that it gets transformed again over here. And by the end, if it's going to work, by the end, we've somehow rearranged the input space so that it can now be categorized in a linear way. And that may involve combining some of the original inputs, rearranging them, moving stuff over here and over there. We kind of move things around until we have a way to classify it that's linear. So that's kind of cool. And it's often, it's well understood mathematics, but it's still a bit of an art to get the thing to do what you want it to do. And it often takes a little bit of trial and error to get it right. And on top of that, because we tend to use random starting states, an individual network, if you run it 3 times, might converge to a solution that's like 80% accurate one of those times, and the other 2 times it can't get anything done. It seems to get stuck at 50 or 60%. Okay, so that's being called stuck in a local minimum. And that can happen to networks, is that if you don't start them in the right state, they're sort of exploring this landscape, and you can think of it, a local minimum. The idea is it's trying to find the valleys in the landscape. So it falls kind of downhill The weights kind of make it fall downhill, and then it might get stuck here, but there's a deeper hill over here that gets it closer to the solution. But it's stuck in this hill. It doesn't want to go up the slopes. It's not hill, sorry. Stuck in this valley. It doesn't want to go up the slopes to get over and into the next valley. That's called being stuck in a local minimum. So typically you also have to run a neural network architecture a bunch of times. And if you want to use one of these architectures in a task, then you run it a bunch of times and you pick the best one. Okay. All right, that's the basics. What I want to do now is I want to go to a sandbox that you can play with and sign off and let you play with it without saying too much more. So if we go into the modules here, we are in week 10. If you just click on TensorFlow Playground here, I have to open it here. Ugh. Hopefully when you go to it, you'll actually see this. Okay, yeah, I think I'm stuck on an old version of the link. So you should see this. This is kind of the default architecture of the network. So let me show you what's going on. We have two inputs, x1 and x2, and we have two hidden layers, and this is the output layer. And what they've done is they've blown up the output layer to show you how it's categorizing. You have a bunch of parameters up here. Some of them you'll recognize: learning rate, activation, you might have a sense of what that is, regularization, and so on. You feel free to play with them all, but leave it as a classification problem. Don't bother to make it a regression problem. And these are the number of epochs it's trained here. Notice the 6 digits. And then this is the data. So you can choose a data set that you want to use. Here's a very easy one. This data set can be classified by a linear classifier. So when I hit run here, it converges very quickly, and I can pause. And so what it's showing here is that these are the orange points and these are the blue points, and this is the decision boundary essentially that it's formed. In the middle there it's unsure, but over in this region it's pretty sure that it's orange, and over in this region it's pretty sure that it's blue. So if the blues are the 1s and the oranges are the 0s, actually it's going from -1 to 1. So it's saying -1 for this class and 1 for this class over here. And you can actually explore the individual neurons. So this has 2 hidden layers. There's 4 neurons in the first hidden layer. And you can see how each of them have learned to classify the task. And 2 neurons in this layer and how they've classified the task. You can see the weights here. So the weight there is 0.99, 1.3. So blue and thick means high and positive. Orange and thin means not so high and negative. So -0.32. So blue, orange is negative. Orange is one class, blue is the other class, basically, negative versus positive. And you can see all the connections between them. Now this network does not require hidden layers, right? Because it's linearly separable. So what I can do is I can go down to 1 hidden layer, reset the network over here, and then hit go, and you can see it converges pretty fast, 91 epochs. And this is the output function. This is like the error rate up here, and you can see it drops really fast. If I reload, pause, you can see it goes straight to the solution. Okay, and so the other ones, though, are harder. So this is impossible for a linear classifier. There's no straight line you can draw here. If I hit go here, we can let it run forever. That's the best that it can do. If I reset again and hit go again, it looks slightly different, but it gets stuck here. It can't do any better than that because there's no straight line it can draw through here that's going to separate this task very well. So for this one, you'll need to add hidden layers. And then in the layers, so here's 1 hidden layer with 4 inputs. Here's 2 hidden layers. One of them has 4 and one of them has 3 inputs. One thing I don't want you to do, at least right away, is let's not work. These are what are called kernel functions. The 2 inputs are just x and y, so let's just stick with x and y for now. But what I want you to do is go through these harder tasks. There's a really hard one. It's got to somehow separate the inside from the outside. Here's a really hard one too. This is probably the hardest. It has to learn a spiral. So the blue points are in the inner spiral and the orange points are in the outer spiral. You can play with learning rate. You can play with this activation. If you want to, you can play with these regularization parameters. We're not really, that's a bit beyond the scope of what we're doing, but it's there. And what I would like you to do is find a network that eventually, and sometimes it might take a while, you might have to run it for a while, but find a network that solves each of these problems. And what I would like you to do is when you've got a network that solves it, maybe jot down the parameters of it. You know, what was your learning rate? What was your activation function? How many hidden layers? how many neurons in each hidden layer, and so on. But then try to get the smallest network that will solve the problem. Smallest in terms of number of neurons. So, you can go each of these layers, you can have 6 hidden layers, and each hidden layer can have 8 neurons in it. This may take a long time to train. The bigger the neuron, the network, the longer it's going to take to train. But in theory, it ought to be able to solve any task. But what I would like you to try and find is just kind of slowly build up and play around with it and think about, what's the smallest network I can find that's going to solve these problems. So I just want you to play with it at this point. And yeah, so I would like you to stop the video, and play around with this for each of these harder problems, each of these 3, and see if you can find a network that solves it. Here's your reset button. Here's your go button. So see if you can find a configuration of hidden layers mostly, although you can play with these other parameters, that solves this, each of these networks. And if you get them, jot them down, and we're going to debrief it in class. So I'd like to hear what networks did you find in class that solved this problem, solved these various problems, and then we can go over it in class and compare. Okay, so that's your task for now. There's a couple more videos to come, each with their own task, I think, and I'll see you in the next video.